So, hello and welcome to a new lecture on statistics. So, the aim of today's lecture is to introduce the normal distribution. And the normal distribution is a very particular distribution in the sense that it is used in many areas in natural sciences and also in social sciences. So, in general, we saw in the previous lectures that a distribution is basically a function that describes how many times on average a certain outcome of a random experiment is obtained. The normal distribution is rather motivated by empirical observations than by a particular random experiment. So, for instance, in natural sciences, like in physics, a temperature distribution, for instance, temperature measurements are usually normally distributed. Also, the height or weight of a newborn baby follows usually a normal distribution. And there are many more examples of this. So what we can actually say is that the normal distribution has its origin, or is rather motivated by empirical observations rather than a particular random experiment. And the normal distribution is also sometimes called the Gauss distribution, called after the famous German mathematician Carl Friedrich Gauss. So maybe we can also write this down. It's sometimes called a Gauss distribution. And it is also sometimes called, because of its particular shape, it is called a bell distribution. And that's because it has obviously the form of a bell. So we can basically represent it here. The typical shape of the normal distribution, so on the y-axis we have the probability density f of x, and on the x-axis we have the random variable x. And then somewhere here we say that we have the expected value mu of the distribution. Let's say that it has this particular height here at this particular random variable x equals mu. And then, as I said, it has this very typical bell-shaped distribution. And most of the values actually are, most of the measurements in a physical experiment or in the social sciences are then basically peaked somewhere around here. So peaked around this area here, this central region here. And of course it is a continuous distribution. In contrary to the ones that we described in previous videos, this one is a continuous distribution. That's the reason why we actually have here a density function and not the probability. So basically it continues here, and it has very small values. So most of the values are centered around the expected value. And we also saw that if a distribution has like a small standard deviation or a small variance, actually the standard deviation is just the square root of the variance, then the shape is much more narrow. And if it has like a very large standard deviation, then basically the different measurements, they are widely scattered around this central value of the expected value. So what we can actually say is that it has this bell-shaped distribution, and the random variable x, they follow, in this particular case, so that's what we assume, a normal distribution law with some expected value mu and some variance sigma squared. And the formal distribution law is given by the density function. So a random variable x equals x is 1 divided by the standard deviation times 2 pi square root of it multiplied by an exponential function to the power minus x minus mu minus the expected value divided by 2 times the variance. So that's actually the probability law or density function of a normal distribution. And so what we can actually show is that this particular density, probability density, is normalized. So in order to do so, we will actually use a property, namely the property of the so-called Gauss integral. And as this is a continuous distribution, so we can actually apply and sum for all the different random variable x equals minor x, we can sum. So basically summing in continuous form means integrating. So we actually have here the integral running from minus infinity to plus infinity times the measurement d of x times the probability density. So basically we copy here 1 divided by sigma 2 times pi multiplied by the exponential function e to the power x minus mu squared divided by 2 times sigma squared. Okay, so basically with this we can actually show that this can be written in the following way. So basically what we can do is we can use this particular property and what we are going to use is the Gauss integral, and the Gauss integral tells us that the integral running from minus infinity to plus infinity of some exponential function to the power e minus a x plus b squared equals pi divided by a and the whole fraction square root of the whole expression. And that's what we are going to use here. So basically we can take this constant factor out of the integral, put it in front, and then basically what we get is, if we identify a, so a basically is 1 divided by 2 sigma squared. So what we have is we have to copy the pi here and then add the expression for a, which is 1 divided by 2 sigma squared, and we take the square root of the whole expression. And with this we basically obtain this factor here, which we are going to copy times 2 pi times sigma. So basically this and this simplifies, and this simplifies as well. So what we obtain finally is 1. So this is basically what I mentioned. This is a normalized distribution density function. Okay, and then basically what we had here is the expected value in the expression, and that's basically the region where most of the values lie around. So it's the central region. And then of course we have the standard deviation, or the square of the standard deviation, which is the variance, and that particular quantity tells us how the measurements are scattered around this central value here. Okay, so that basically terminates the explanation video on the normal distribution. If you have additional questions or remarks, then please leave a message under the video, in the comment section under the video. If you want to know more properties of the normal distribution or some additional examples, please let me know, and like my video and subscribe to my channel in order not to miss a future video. Thank you.